Welcome. Today, we're going to explore one of the most fundamental concepts in machine learning, linear regression. Imagine you're trying to predict the price of a house. What's the most important factor? Often, it's the size. Let's say we collect data from several house sales. We plot the size of each house on the x-axis and its price on the y-axis. Each dot on this scatter plot represents one house. As you can see, there's a clear trend. As the size increases, the price tends to increase as well. The core idea of linear regression is to find a single straight line that best represents or fits this data. This best fit line is our model. We can use it to predict the price for a new house size that we haven't seen before. This line can be described by a simple mathematical equation, which you might remember from school. In machine learning, we often write it like this. Let's break it down. H stands for hypothesis, which is just a fancy word for our model's prediction. X is our input feature, in this case, the size of the house. Theta 0 is the intercept. It's the predicted price if the size were 0. Think of it as a base value or a starting fee. Theta 1 is the slope. It tells us how much the price increases for each additional 1,000 square feet of size. It determines the steepness of our line. The goal of linear regression is to find the perfect values for theta 0 and theta 1 that create the best possible line for our data. But what does best possible line even mean? How do we measure it? We measure the error for each data point. This error, called a residual, is the vertical distance between the actual data point and our prediction line. We want to make these errors as small as possible on average. To do this, we use a cost function. Let's build it step by step. First, the error for a single data point, I, is our prediction minus the actual value. We square the error so that positive and negative errors don't cancel each other out. Squaring also penalizes larger errors more heavily. Next, we sum up these squared errors for all of our m data points. Finally, we find the average by dividing by m. This is the mean squared error, our cost function, which we call j. The 2 in the denominator is a mathematical trick to make later calculations cleaner. Our objective is simple. Find the values of theta 0 and theta 1 that make this cost j as small as possible. Let's make this concrete with some numbers. Suppose we have 3 data points for house size versus price. Let's test a random line, say with theta 0 equals 0.5 and theta 1 equals 1. Let's calculate the cost. For x equals 1, prediction is 1.5. Error is 1.5 minus 2, which is negative 0.5. Squared, that's 0.25. For x equals 2, prediction is 2.5. Error is 2.5 minus 4, or negative 1.5. Squared is 2.25. For x is equal 3, prediction is 3.5. Error is 3.5 minus 5, or negative 1.5. Squared is 2.25. The total cost j is the sum of squared errors divided by 2 times m, which is 6. The cost is about 0.79. An algorithm like gradient descent would find the optimal parameters. For this data, they are approximately theta 0 equals 0.67 and theta 1 equals 1.5. If we recalculate the cost with these optimal parameters, we would find a much lower value, indicating a better fit. Once we have our best fit line, how do we know if the model is actually any good? The cost, j, is an absolute number, which can be hard to interpret. For this, we often use a metric called r², also known as the coefficient of determination. R² tells you the proportion of the variance in the dependent variable, price in our case, that is predictable from the independent variable, size. It's a value between 0 and 1. And r² of 0.9 means our model explains 90% of the variability in house prices. This is very good. An r² of 0.1, however, means our model only explains 10%. This suggests that size is not a very good predictor of price on its own, and our model is not very useful. A critical concept in machine learning is the danger of creating a model that's too complex. This is called overfitting. On one hand, we have a simple linear model. It captures the general trend of the data, but doesn't perfectly hit every point. This is a good fit. On the other hand, we have a very complex, wiggly model. This model learned the training data perfectly, including all the random noise. This is overfitting. While it has zero error on this specific data, it has learned the noise, not the underlying pattern. It will likely make very poor predictions on new, unseen data. Often, a simpler model that generalizes well is much more useful than a complex one that overfits. So, let's quickly recap. Linear regression is a simple yet powerful tool for finding a linear relationship between variables. When should you use it? First, when you have reason to believe the relationship is linear. Always visualize your data first. Second, when you value interpretability, it's very easy to explain to someone what the slope and intercept mean. And finally, it's an excellent baseline model. If a very complex model can't perform better than simple linear regression, you might be on the wrong track. That's linear regression, a fundamental building block for any machine learning journey. Thank you for learning with us today.